Hi everyone. This lesson is on ordinary annuities, which is our second financial application in this unit. An annuity is a series of equal deposits or payments made at regular intervals of time. An ordinary annuity is an annuity in which the deposits or payments are made at the end of each time interval. An annuity can be thought of as a geometric series, and our ordinary annuity formula is the amount in the account A, or the amount in the annuity A, is equal to R, which is the amount of our regular deposit, times 1 plus I to the n, which looks familiar to our compound interest formula. Where I is the interest rate per compounding period expressed as a decimal. N is the number of compounding periods. And those are the things that you need for the formula. So just going to remind you that the financial application we've already done was compound interest. And the formula for that was A equals P times 1 plus I to the power of n. And the big difference between the two is that in this case, we only put money in one time. So we put money in, we call that our principal. We invest it for a number of compounding periods with an interest rate, and we leave it there, and then after a certain amount of time we see how much there is in the account, and it's more than if we just put them, remember I said if we just put that principal under our mattress it would stay the same, but because of compound interest our amount increases with time. So ordinary annuities, we're not just putting an amount in one time, we're putting it in regularly. That's why we use R instead of P, because that's our regular deposit. So here's our first example. Kara invests $1,000 at the end of each year in a Canada savings bond that earns 6.5% interest compounded annually. How much would be in the account after 12 years? So similar to our compound interest, we're going to look and see what things in this formula we know from the question. So you should see that we're depositing $1,000 at the end of each year, so more than once. That's what clues you in that we're talking about an annuity here, not just plain old compound interest, because we're not just investing the money one time, we're putting it in at the end of each year. So our regular deposit is $1,000. And our interest rate expressed as a decimal is 0.065 divided by 1 because it's only compounded one time a year. And how much would be in a savings account after 12 years? So N would be 12. So now we go to our formula. A equals R times 1 plus I to the power of N minus 1 over I. And we want to substitute in the values that we know. So our R is 1,000. 1 plus I, 1 plus 0.065. If you want to just write 1.065, you can. And to the power of 12, subtract 1 over I, which is 0.065. Similarly, like I know you can subtract 1 in your head. I know you can add 1 in your head too if it's an easy decimal. I'll show you what to do if we have to leave it as a fraction with a calculator. So now we can type this into our calculator. I would type it as I see it. So I'm going to go 1,000 times bracket 1.065 to the power of 12 minus 1 closing bracket, and then I usually press equals or enter, in this case equals, and then I divide by 0.065, and that gives me $17,370.71. Okay, now I want to show you the difference between this annuity here, whereas if we just put $1,000 under our mattress 12 times in a row, we'd have $12,000. But by investing it in this annuity, we end up with $17,370.71, and that extra $5,370.71 is just from the interest, the 6.5% interest per year. Okay, so you can see why investing is better than just storing the money in a safe. Okay. All right, so our next question. William deposits $225 at the end of each month into an ordinary annuity. If the money earns 5.99% per annum compounded monthly, how much money is in the account at the end of 3 years? So again, we're going to pick out the things that we recognize here. And first of all, we're depositing each month, so we know we're talking about an annuity as opposed to just plain compound interest. And that regular deposit is $225. I is 0.0599, but we have to divide by 12 because we're compounding monthly. And we can check if that's a nice number. If it's not, we let our calculator do the work for us. It's not, so we're just going to leave it like that. And N is going to be 3 years, but times 12 months in a year, so that's 36 times interest will be calculated. So again, we're using the same formula. But it's going to be slightly more challenging to calculate because we've got our fraction here. So we have 225, bracket, another bracket, 1 plus, see it's not easy to add that in our heads, so we're going to let our calculator do that for us, over 12 to the power of 36 minus 1 over, and now since I'm dividing by a fraction, I'm going to keep it in brackets as well, 0.0599 over 12. And I'll show you how our calculator can do all that work and keep it as exact as possible without rounding until the very end. Okay, so I'll do it on 2 different calculators. Here's my calculator where I can see everything that I type. So 225 times opening bracket, and then there's another opening bracket. 1 plus 0.0599 divided by 12, closing bracket, over means divided by, to the power of 36 minus 1, another closing bracket, and then I usually press equals here, divided by, because this is a big divide by here, opening bracket, 0.0599 divided by 12, closing bracket, equals. So that says the amount would be $8,849.30 if we round to the nearest hundredth, which you would with money. Okay? So that's how much William would have if he puts $225 at the end of each month into an account, compounded monthly. All right, let's do it on a calculator that's a bit more plain. We can still do the same thing though. So 225 times opening bracket, 1 plus 0.0599 divided by 12, closing bracket, to the power of 36 minus 1, closing bracket, equals, divided by opening bracket, 0.0599 divided by 12, closing bracket, equals. And you can see we get the same answer there, even though we can't see every single number we put in because it's not a graphing calculator. It's a smaller display. So make sure you can get that on your calculator. If you can't, rewind and go through step by step. Maybe ask your someone sitting beside you to help you keying it in. Okay, and then so we're seeing that I just want to show you, you don't have to calculate this, but I just want to show you if we just did $225 and put it under our mattress 36 times, we would end up with 225 times 36, $8,100. But because of interest, we're getting this extra $749.30, and it's only 3 years, so that's decent. Okay, so again, interest is important to increasing money, especially over a long time. Like if we change that 3 years to 30 years, we would make a lot more money. Interest. Okay. Cecilia deposits $1,500 each year for 5 years into her RRSP. The plan earns 6.88% per annum compounded annually. She makes her deposits on her 19th, 20th, 21st, 22nd, and 23rd birthdays. If she makes no further deposits, how much will be in the account on her 65th birthday? This is a two-part question because the first part of it, for the first 5 years, it's an annuity because she's putting the $1,500 in each year for 5 years. But then she's just leaving it there. So that becomes just plain compound interest. So we're going to divide this into two questions. The first part is our annuity part. And that uses our formula. A equals R 1 plus I to the power of n minus 1 over I. And she's putting in $1,500. And then I is going to be 0.0688, right? Because I'm only dividing by 1 because she's putting it in per year. So I can actually add 1 to that very easily and make that 1.0688 to the power of, she's only doing that 5 times, minus 1 over 0.0688. So now I'm going to get my calculator out and I'm going to do 1,500 times opening bracket 1.0688 closing bracket to the power of 5 minus 1 closing bracket equals divided by 0.0688 equals. And that's going to give us $8,605.48. And okay, so now she's just leaving it there. So now we're on part 2. She's leaving it there until her 65th birthday. So she's not putting any more deposits in. And she's going to carry this over, and that's going to become the principal. So we're going back to this formula. So the amount in the account, she's investing this $8,605.48 and just leaving it there, times 1 plus I to the n. Okay, so she's starting off with this amount that she saved up over those 5 years. And then the interest rates, it's going to stay the same, so 0.0688. Now, how many years does she leave it there for? So from 65, from 23 to 65, so minus 23 here actually. It's going to be our n, which is going to give us 42. So n is going to be 42. So she leaves it there for 42 years. And now, without contributing any more, we'll see how much she'll have after 42 years. So that's going to be 8,605.48 times, I can add those in my head, 1.0688 to the power of 42. So that's going to give her $140,742.67. Okay, so just over those 42 years, so just accruing interest only, okay? We started with this much. Just by accruing interest and leaving it there for 42 years, she now has $140,742.67. And that shows you if you start saving for retirement really young and aggressively, then you will have a lot of money just based on interest alone. Okay. Question 4, when Ken retires in 5 years, he plans to take a trip to Australia. He wants to contribute to an ordinary annuity that pays 6.3% per annum compounded monthly. If he needs $10,000 for the trip, how much money must he invest each month? So this time, we know that he wants to have $10,000 for his trip, but we don't know R. So what I would like to do is rearrange this formula. We know we're talking about an annuity because he wants to put the money in monthly. So if we look back here to our first page, if we take this original formula and we want to get R by itself, I would first multiply both sides by I to undo the dividing by I. So these i's cancel out. And I have that A times I is equal to R times this big bracket. And then if I divide both sides by that bracket, which is 1 plus I to the nth minus 1. I've got a formula that R, the regular deposit, is going to be A times I over bracket 1 plus I to the power of n minus 1. So that formula we can use when we're calculating the regular deposit for an ordinary annuity. Okay, so we've just rearranged this formula. So instead of solving for the amount in the annuity, we're solving for what that regular deposit would have to be if we know the amount we want after a certain time period. So I'm going to use that formula for Ken's question. So R equals A times I over bracket 1 plus I to the power of n minus 1. So now what's my I going to be? I is going to be 0.063 divided by 12. We'll see if that's a nice number. So 0.063 divided by 12 gives me 0.00525. So it is a nice number. You can see that little -3 there, that's scientific notation. It means to move the decimal 3 places to the left. Or some of you, if you want to see again here, this one will show you the decimal. 0.063 divided by 12, 0.00525. And if you want to borrow one of the graphing calculators up at the front to do your calculations, then please do that. Okay, so now I'm going to substitute in. So I've got my A is $10,000 times 0.00525 over, I can add the 1 and the 1.00525. Oh, we didn't figure out n, sorry. So it's 5 years, 12 times a year. So that's going to be 60 to the 60th minus 1. And then I'm going to type that into my calculator. So I'm going to go 10,000 times 0.00525 equals, divided by opening bracket, 1.00525 to the power of 60 minus 1 closing bracket equals. It's very important you put the whole denominator in brackets. Okay, so that's going to give you $142.23 if we round the 6 up, or round the 2 up from the 6. So that means Ken needs to deposit $142.23 at the end of each month. And if he does that, he'll have the $10,000 he needs. Oops, didn't show you my, here we go. And let's see, if we just multiply 142.23 by 60, the number of times he deposits, we get 8,500 about, so we're getting about $1,500 just from interest. And that's just over 5 years. So again, the longer you invest, the more interest you'll get because we're compounding it. Interest on interest. Okay, question 5. Mallory's parents have saved for her education by depositing $500 semi-annually into an annuity that pays 6.85% compounded semi-annually. If they made their first deposit on January 31st, 2010, how much money will be in the account on December 31st, 2027? Okay, so we want to know A, so let's write out our formula. We know it's an annuity because they're doing it more than once. So they're saving $500, or they're investing $500 twice a year. So I is going to be 0.0685 divided by 2. Which is 0.03425. And the number of times is going to be, okay, so we have to figure out how many years this is going on for. So the end of the first month of January, so all of 2010 till the end of 2027. So we're going to do 2027 minus 2010. And then, so that's 17 years, 12 times a year. So that's 204 times they're going to end up investing. So we've got our amount's going to be 500 times, so I can add 1 to that, 1.03425 to the power of 204 minus 1 over 0.03425. All right, so let's use our calculator now and figure out how much they'll have saved. So we're going to do 500 times 1.03425 to the power of 204 minus 1 equals, I should have closed the bracket, but I know that's the same, divided by 0.03425, and that's gonna, nope, must have made a mistake there keying it in. 0.0685 divided by 2. Oh, I know what I did. This should have just been times 2. My bad. This is only 34. It would be nice, but they only invested, or they only put the money in 34 times, not 204 times. So that's going to make a big difference here. Sorry about that. All right, so it's going to be 500 times 1.03425 to the power of 34 minus 1, closing bracket, equals, divided by 0.03425. So that will give them $31,276.60 that they'll have saved up. So therefore, there would be $31,276.60 in the So that's saving $1,000 a year, like $500 twice a year for 17 years into an investment account that has a pretty good interest rate. If you just did 1,000 times 17, you'd just have 17,000, right? But because of the amount of time over 17 years, you actually have 31,000, which is almost twice as much. So interest is good, and it's good to save. And over time, that amount of interest you get really makes a difference. Okay, so our last question, Calvin wants to save $500,000 in 7 years in order to put a down payment on a house. How much should he invest at the end of each month into an ordinary annuity that pays 6.08% compounded monthly? So again, this time we know A, and we know that it's an annuity because he wants to invest at the end of each month, not just one time. So R is what we're looking for. And we already rearranged our formula so that when we're finding R, we use this version of the formula. So R equals A times I over 1 plus I to the power of N minus 1. Sorry, R equals R. R equals question mark. What else do we know? I is 0.0608 divided by 12. Which is not a nice number, so we're just going to leave it and let the calculator do all the rounding for us at the end. N is going to be 7 times 12, which is 84. So the regular amount that Calvin's going to have to put in to save up $500,000 in 7 years at the end of each month, we can find by doing 500,000 times 0.0608 divided by 12 over bracket 1 plus 0.0608 divided by 12 to the power of 84 minus 1, closing bracket. Okay, so again, we want to key this in very carefully using brackets. So 500,000 times, so bracket 0.0608 divided by 12, closing bracket, equals, divide by opening bracket, another opening bracket, 1 plus 0.0608 divided by 12, closing bracket, to the power of 84 minus 1, closing bracket, equals. So that means he's going to have to deposit $4,790.13 at the end of each month in order to have saved $500,000 in 7 years. Okay, and then we can see if we didn't have interest, if we were just saving that money in our mattress, we multiplied by 84 times, we would have 402,371. So the difference to that 500,000 is all interest based, and that's only 7 years. Okay, and then so therefore Calvin would need to deposit $4,790.13 at the end of each month. Okay, so try the practice questions. And make sure you check your answers at the bottom of the back page. And again, use the graphing calculators up at the front if you're having trouble typing it into your regular calculator. And you should be good.